Okay, I guess we'll get started. So just to quickly remind you of where we left off last class, we were talking about implementing equals for a value type class. Now remember what happens if you don't provide an equals method in your class, right? When you write x equals y, what ends up happening is you get the object version of equals, right? And the object version of equals is exactly equivalent to x equals y, right? And that means, right, do x and y point to the same object. And for value type classes, things that represent something like a physical quantity, like a time or a date or a point or a counter, you probably want to know, do two objects have the same state, right? And so if you want to know, do two objects have the same state, that's when you override equals. So here's the version of equals for the counter class, right? Remember our version of equals, you have to implement in a very particular way in Java in order to get it to work correctly. Right, so there's one requirement, the first one, right, where the first if statement that tests is an object equal to itself, right? So an object should always be equal to itself, right? X equals x should always be true. So that's what our first if statement checks. Our second if statement tests whether or not y, in this case, is null, right? So an object is never equal to null and never throws an exception. So we check, is obj equal to null? And if so, we return false. In the version of equals that I showed you on Thursday, we said that two objects can be equal only if they have the exact same type. So we use the getClass method to determine the class of each object. And if they're the same, if they're different, we return false. And finally, once we've done all that, we know that that thing obj, in this case, it really is a counter object, right? Despite the fact that in the parameter list, obj is a big O object. Right, so we convinced the compiler that obj is in fact a counter object. We cast obj to a counter, and then we can go ahead and get its value. Right? We can't get its value here. So we can't get the value here until we do the cast, because as far as the compiler is concerned, obj is a big O object. Right? And big O objects, they don't have their own fields that you can access. Right? But at this point here, right, once I pass that last if statement, I know that obj is in fact a counter object, so I can safely do the cast. Right? Now, unlike C, that cast in Java will fail if obj is not a counter object. Right? C will happily take the cast and just cast it. The compiler might warn you, but I doubt it will. In Java, you'll get an error. So this will throw an exception when you try to do the cast, which is not good because equals is not supposed to throw an exception. And then at that point, you can finally compare the value of the two counters. Right? So the pattern is always the same when you implement equals, except there is a second way, a second correct way to implement equals, which I'm going to show you today. If you've been reading along in the notebooks, then this is the version of equals that's shown in the notebooks. Right? So this is equals using the operator called instance of. Right? So that previous version of equals that I showed you is perfectly fine if the class that you're using, if your class is never going to be used as part of an inheritance hierarchy. We'll talk more about inheritance, I think, in a week or so. If your class is going to be used in an inheritance hierarchy, then you should do what I'm showing you today. Right? And this is the same version that I've shown you in the notebooks. It's also the exact same way that it's described in this book called Effective Java. Joshua Block is one of the principal architects of the Java language. So he kind of knows what he's talking about. When he writes something, it's worth listening to him. That book, if you actually do any professional programming in Java, and you're engineers, so I don't know how many of you actually will, but if you do, that is highly recommended reading. Right. Okay. So here are requirements for equals, this time using instance of. Okay? So they're the same as before, right? An instance is always equal to itself. An instance is never equal to null. And in today's lecture, so in the previous lecture we said that instances with the exact same type can be equal. Now we're going to relax that requirement. We're going to say instances with what are called compatible types can be equal. This will make more sense to you in a week or so, but for now, just go with it. And then finally, part 4 is exactly the same as before, right? Instances with the same state are equal. So since parts 1 and 2 are exactly the same, the slides are exactly the same, right? X equals X is always true. X equals Y should be true if X and Y point to the same object, right? And if you want to know if two objects point to the same object, you just use equals equals. Right? So the first part's still the same, right? If this equals this equals OBJ, return true, because you've effectively written X equals X. Right? An instance is never equal to null. So this part changes a little bit because we don't actually have to check explicitly is OBJ equal to null. And that's because what we're going to do in part 3, we get that check for free. Right? So this changes now. So the second if statement's not here anymore. Instead, we're going to replace it with a third if statement. Well, I guess this will be the second if statement in this implementation of equals. We're going to use this operator called instance of. Okay? So the way you use instance of is you have a variable here. Right? So this could be X. And then over here, you've got some type name. So this could be .2, or it could be string, it could be list. Right? So this is any reference type on the right-hand side. And that operator returns true or false. Right? So instance of returns true. So let's do it this way instead. So the instance of operator tests if a reference refers to an object that implements a specific interface. So remember our list. Remember the list. List is an interface in Java that represents things like linked lists and array-based lists, right? So array list. So if you had an array list over here, an array list variable here, and you wrote that list instance of big L list, that would return true, right? Because our array list implements the list interface. It also behaves the same as getClass. So if I have a .2 object here, right, and I write .2 over here, right, so is X an instance of .2, that will also return true. So it will also return true when getClass returns true, right? So if the object is an instance of or is an object of the class over here, then it returns true. So in that sense, it behaves exactly the same as getClass. But there's a difference. And it's this third one here that becomes important next week. So it also returns true if that thing there is a subclass of that thing there. So you don't know what a subclass is yet, which is why it's kind of weird to put this, it's kind of weird to be talking about this at this point in the course. But we're talking about equals, so we might as well get it done now. So next week, you'll learn about subclasses. Might be later this week, actually. But you'll learn about subclasses, and then this part will make sense. For now, just assume this is the same as getClass. Right? And also, if that thing there is null, then instance of always returns false. So you don't have to check whether or not OBJ is null, right? Because instance of will do it for you. So what we want to check for is OBJ an instance of the class that we're implementing equals in? Right? So for .2, we want to check, oh yeah, this is wrong, sorry. This is OBJ. So in this case, we want to check, is OBJ an instance of .2? And in fact, we're going to check the opposite. Right? So if OBJ is not, right? So there's a not operator here. So if OBJ is not an instance of .2, then return false. Right? So in this case, OBJ is not a .2 object. So it can't be equal to another .2 object. Right? So that combines steps 2 and 3 from the previous lecture. And then finally, instances with the same state can be equal. So this is all the same. Right? So you do the exact same thing as before. Right? You do your cast, and then you check for equality of the fields. .2 is, because it has these double fields, you have to do this double to long bits nonsense in order to get it to work the same as any other equals method in the Java standard library. Right? So go back and look at the previous lecture slide if that's confusing to you. Right? For now, I'm just going to keep on going. Unless anybody has any explicit questions about this slide. Anybody? Okay. And so those are the two different ways to implement equals. Right? They're very similar, It turns out, though, that this version of equals is the one that you want to use when you're implementing more complicated structures of more complicated families of classes. Right? Everything we've done so far has been very simple, so you just use getClass. In a couple of weeks or so, you'll want to consider switching to instance of. All right, moving around. Now, have you guys talked about hash tables in your previous data structures course? Sort of? I see sort of and I see yes. Okay, so let's go with sort of, and we'll review what's going on here. All right, so we've been talking about overriding equals, right? Now it turns out there's a related method in Java called hashCode. If you replace equals, then you also have to replace hashCode. Otherwise, these things based on hash tables in the Java language, none of them work anymore. They don't work properly. They still sort of work. They don't work the way you would expect them to, and it becomes very hard to debug your code if you're trying to use one of these hashed-based structures. Right, so remember in the hash-based structures we've seen are hash set and hash map, right? Linked hash set and, linked hash set and linked hash map as well. Right, these are all based on hash tables. Okay, so if we haven't replaced hashCode yet in point 2, right? We replaced equals, haven't replaced hashCode. So I can make a point 2 object, P, right? Its coordinates are 1 and -2. And then I can make a hash set or a hash map, it doesn't matter, right? Any of the hash containers will do. And I can add P to that set H, right? If I ask the set H, right, do you contain P, the set will tell me true. So I say, yeah, it contains P, you just put it in there, so it should contain P, right? Now the weird thing that happens is, if you make a new point 2 object that has the exact same coordinates as P, right, so they're both 1 -2, and then you ask the hash set, do you contain the object Q? The answer is false, right? Even though those 2 points are equal. Right? So for the value type classes, most people are going to expect that if you put a point or an object into a hash set or a hash table, right? If you ask the hash set or hash table, do you contain an object that's equal to the one you just put in, it should return true. Right? But in this case, it returns false. Right? So this is going to go against the way everybody's expecting this method to work. Everybody's expecting the hash set to work. All right, so what's going on here? So let me back up to a list or an array. Right? So suppose you have a list or an array of unique points. Right? So they're all unique, so no 2 points in the list or array are equal. Right? I want to know, does that list or array contain a particular point? Right? You want to do search on the list or array. Right? Now you can just use the contains method if you wanted to, if you had a list. Right? But if you wanted to do this on your own, you'd just write a loop. Right? So you'd write a loop, you'd look at every element in the list or the list or array. When you found one that was equal to the thing you were looking for, you would return true and stop. Right? If you look at everything in the list and you don't find something that's equal to the thing you're looking for, you would return false. Right? So you just write a loop. I'm going to write a little static method here called hasPoint. Could also call it contains, but whatever. Right? So does that list points have a point equal to P? Right? So that's the question you want to answer. You can all write this, right? You just loop over the list of points. Right? If you find a point that's equal to P, return true. If you look at all the elements, if the loop finishes and you don't find one that's equal to P, you return false. Right? Easy peasy. So that thing there, that's just called exhaustive search, or linear search, or sequential search. Right? It has a bunch of different names. If you double the length of the array or the list, right, then that potentially doubles the amount of work you have to do. Right? Because if the point's not in the list, then you have to look at every element in the list. Right? So if there are n elements in the list, then in the best case, you look at the first element, and the first element happens to be the thing you're looking for, so you return true. Right? There's one called equal. In the worst case, you have to look at everything in the list because the thing you're looking for is not there, or it's the last element in the list. Right? And that requires n calls to equals. And on average, you would end up calling equals roughly n over 2. Right? So if you had a bunch of lists that were all randomized and you were looking for a point that was in the list, then on average, it would be n over 2. Right? And you probably know that's in big O of n. Right? Okay, now how do hash tables work? So hash tables you can think of as being a list or an array, right? Except instead of only being able to store one element at each location in the hash table, you can store many elements, right? Or an arbitrary number of elements. Right? So just think of this as being an array where I can put more than one thing into each, in this case I'm calling them buckets. Right? So these big rectangles are buckets, and I can put multiple references in each bucket. Right? If I want to put something into the hash table in Java, right? So the way it works in Java is I want to insert some object A into the hash table. Right? So I say h.add A. Right? Then my hash table takes A and uses its hashCode method. Right? So what hashCode does is it takes an object and somehow converts it to an integer value. Right? How that conversion works we'll describe later on. Right? But you have some object, right? And you map that to some int value. That's exactly what hashCode does. Right? And it could be negative or it could be positive, right? Because ints are signed. So what the hash table does with the hashCode value is it does something to the value so that it fits between 0 and n. Right? So that's what that red arrow means. Right? Take whatever hashCode returns, do something to it so it fits between 0 and n, and that's the bucket that we're going to put the object into. Right? So A, call hashCode, hash table does something with the value and ends up with 2. So that means we're going to put A into bucket labeled number 2. Right? So it goes into that bucket there. And that just happens for everything you try to put into the hash table. Right? I want to put B into the hash table. Now remember, all these things are unique, right? So none of these things are equal to one another. So B, right? So I call add on the hash table. Hash table takes the object, calls hashCode, does something to the value, and in this case we get 0. So B goes into bucket number 0. C, exact same thing, right? Call hashCode on C, do something to the value, it turns out to be n, so it goes into bucket number n. And because this is a hash table, you can put more than one thing into each bucket. So if you put an object D into the hash table, now D and C are not equal, so they're distinct objects, okay? They're distinct objects and they have different values. But it turns out that when you call hashCode on this object and then convert that value to a number between 0 and n, you get the same, you get n, right? Which was the same as for C. So we just go ahead and put the object D into the last bucket as well. Right? And then you just keep on going. Okay, now ideally, the distribution of elements in a hash table is uniform. Right? So in other words, each bucket contains roughly the same number of elements. Right? That's what you want in an ideal hash table. Right? And in a well-designed hash table, that tends to happen. Right? So that's what you want to happen. All right. Now, what happens when you search the hash table? Right? So when you search a hash table, it's different from a list. Right? I don't have to look in every bucket. Right? All you do is you call hashCode on the object that you're searching for and then go look in that bucket. Right? So if I want to know is A in the hash table, you just repeat the process. Right? Call hashCode, do something to the value to get it between 0 and n, and then go look in that bucket. Right? If you find something in that bucket that's equal to A, you return true. Right? And that's easy. Right? So I don't have to look in every bucket. Right? What about Z? So if I try to look for Z, call hashCode on Z, massage its value so it's between 0 and n, and I get n. Right? Well, we just go to bucket n and compare Z to every element in that bucket. Right? So is Z equal to C? The answer is false. Right? Again, remember all of the things I'm putting into this hash table are unique. Now there's more elements in that bucket, so is Z equal to D? The answer is false. Right? Is there anything else in the bucket? The answer is no, so Z is not in the hash table. Right? But again, I didn't have to look in every bucket. I only had to look in one. Right? And if every bucket holds roughly the same number of elements, right, then that implies that the hash table can be very fast compared to a list. Right? So searching a hash table is usually much faster than linear search. Right? If I double the number of elements in a well-designed hash table, typically there's no increase in the amount of time needed to search for an element. Right? Which is amazing. Right? If I double the length of a list, I double the amount of time. If I double the size of a hash table, I don't do anything to the time, which is really remarkable if you think about it. Right? So if there are n elements in the hash table, in the best case, right, you call hashCode on the element, you go and look in that bucket, and there's nothing in the bucket, right? If there is something in the bucket and it happens to be equal to the thing you're looking for, well, then that's good too, right? So that's either 0 or 1 called the equals. Now, in the average, so on average, remember, so on average, every bucket holds a small and roughly equal number of elements, right? And furthermore, in a well-designed hash table, the number of elements is not related to the number of elements in the size. Right? So the number of elements in a bucket is not proportional to the number of elements, to the number of buckets. Right? So that means there's only a small number of calls to equals, right? And that means, in other words, small, not dependent on the size of the, not dependent on the number of elements in the hash table. So that's O1. Now, in the worst case, though, you might end up in the case where everything ends up in the same bucket, right? Which is what you want to avoid in a well-designed hash table, right? But you'll see in a second, in Java, it's possible to force everything into the same bucket, right? Now, if everything's in the same bucket, you have to, when you search for an element, you look at everything in the bucket, right? So that becomes equivalent to using a list, right? So now your search breaks down and becomes ON. Right? So in people who implement hash tables for a living, they try very, very hard to make sure this never happens. Okay, so what happens if you override equals but you don't override hashCode? Right? So, well, the same thing happens that if you don't override equals, right? You get the version of hashCode from big O object. Right? Now, what does that do? Well, that uses the memory address of the object to compute the hashCode. So it uses the memory address of the object to compute the hashCode. So what's the implication of that? Right? Well, this is the same code that I had before. Right? So here's P, it's a new point. Right? So it's some object sitting somewhere in memory. I add P to this hash set. Right? So when you ask H, do you contain the point P? Right? The hash set goes and calls hashCode. hashCode looks at the memory address of P, right? And then computes some value based on that. Now, when I do the same thing with Q, right? So I ask, does the hash table contain Q, right? So hashCode goes and looks at the memory address of Q and returns some value based on that. But Q is a distinct object from P, right? So P is a new point, Q is a new point. That means they have different memory addresses, right? Because you can't put two things in the same memory address, right? If the memory address is different, its hashCode's different, right? If the hashCode is different, almost certainly the location that it appears in the hash table is also different, right? In other words, it appears in a different bucket, right? So P and Q refer to distinct objects. They have different memory locations. Therefore, their hash codes are probably, almost certainly different, but it's possible that they're not, right? And therefore, the hash table ends up looking in the wrong bucket, probably, right? And it does not find, sorry, that's wrong. This is an old slide. It does not find the point that it's looking for, even though P equals Q is true. Right? So that's why you have to replace hashCode, because if you don't, that's why you have to replace hashCode if you replace equals, because if you don't, if you don't, your hash containers no longer work properly. Now here's the problem, right? So your hash containers no longer work properly. If you're testing your class, so if we test the point2 class, right, you can test the current class that doesn't have hashCode till the cows come home, right? And it's always going to pass all of its tests, right? It only fails when you take a point and stick it into a hash table of some kind, right? And it's probably very likely that you're not going to test that case in your unit tests for your class, right? And so the only time you know that there's a problem is when either you or someone using your class tries to use your class inside of a hash collection, right? And then you start getting back these strange error reports saying, hey, look, I'm putting points into this into a hash table and it's not working, right? But now you know, well, the problem probably is you have a bad implementation of hashCode. Okay? So what's hashCode supposed to do? It's supposed to take an object and convert it to an int, right? Now, how's it supposed to do that? Well, the way you're supposed to do it is you look at the fields of the object, and you somehow mash those fields together to get an int value, right? Exactly how that works, I don't really care that you know. Okay? It's not that important. It is described in great gory detail, though, in the notebook. So if you want to know how this works, the notebook explains to you the way that most modern IDEs will implement hashCode for you. right? Okay, but there is something you do need to know, right? Okay, so what you need to know is that the bottom point, right? So if x equals y is true, then x.hashCode must be the same as y.hashCode, right? Because you need the hash table to look in the same bucket for the two objects, right? So if two objects are equal, they must produce the same hash code, right? The other thing is that hash code can't be random, right? So imagine your hash code method was random. Every time you put an object into the bucket, it goes into a random bucket, and that's no good either, right? So hash code must always return the same value if x does not change its state, right? So if you never change the coordinates of a point, that point always has the same hash code value. All right, now what would be nice? So what would be nice is if two objects were not equal, then they produced different hash codes, right? Because that would force the hash table to look in, put the objects into different buckets. But if you think about that for even like 30 seconds, you'll realize quickly that that can't possibly be the case, right? Now, why can't that be the case? So our point2 class has two fields, right? Both of type double. So how many unique point2 objects are there? Well, how many double objects are there? There's 2 to the 64, because every double has 64 bits, right? I've got two fields. So how many unique point2 objects are there? There's 2 to the 64 times 2 to the 64, 2 to the 128, right? How many unique ints are there? There's 2 to the 32, right? So there are way more point2 objects than there are possible hash code values. So it must be the case that two objects that are not equal can have the same hash code, right? You want them not to have the same hash code, but it's physically impossible to do, right? 1 and 2 is what is required by the hashCode method, right? And so what does that mean? So when you implement hashCode, you have to make sure that 1 and 2 are true, right? So if I wanted to do, oh, sorry, this is double, not float. These are double. So if you wanted to implement hashCode for the point2 class, you could do it this way, right? But don't. Right? So that returns 1, right? If 2 points are equal, do they return the same hash code? Yes, because it's always 1, right? Does the hash code ever change? No, it's always 1. So this is perfectly legal, right? Don't do this. So what happens if you do this? Everything goes in the same bucket, right? What does that mean? Your hash table becomes a list, right? What does that mean? Instead of ON search, you get instead of O1 search, you get ON search. You might as well have just used the list, right? So don't do that. Similarly, again, these are double, right? This is slightly better, but it's still bad, right? So I can just add the x and y coordinates together. That gives me a double, right? But then I can just cast that value to an int, and that gives me an int, right? Does this satisfy the hashCode contract? Yes, right? If 2 points have the same coordinates, then the sum of their coordinates is the same. That's good, right? So the hashcodes will be the same. If the point never changes, does it return the same hashcode? Yeah, there's no randomness in this method, so that's fine too. So this is perfectly fine. Well, it's perfectly fine in terms of satisfying the contract for hashcode. Right? In practice, this behaves badly. So if you have an application where everything, all your points are have coordinates that are between 0 and 1, right? Then this tends to put all of those points in one of a small number of buckets, which you also want to avoid, right? So the idea between hashcode is it should try to randomly distribute objects in the hash table. Right? Now, how do you do that in a principled way? Well, it turns out no one really knows. It turns out we have a good idea of how to do it empirically, but no one can prove that the way that we actually do it works all the time. So the way that we do it, if you ask let me show you what, oh wait, I closed Eclipse, sorry. Sorry, just bear with me and let me start up Eclipse. Okay, so the way that this ends up working is you take each field of your object, you somehow convert each field to an int, and then you mash them together by multiplying it with the prime, some prime number. Empirically, this seems to work really well, but no one can actually prove that this produces a good hash code. So there are actually people who study hashing for a living. because it's used not just for hash tables. It's also used for security. So in cryptography, there's a related hashing concept. Yeah?
What's the difference between a hash table, a hash set, and a hash map?
So hash sets and hash maps, they're all built on top of a hash table, more or less. In actuality, the Java's hash set's really weird, because a hash set's actually a hash map in Java, even though it doesn't look like it. But if you actually go and look at the implementation of hash set, internally there's a hash map. So hash set's built on top of hash map built on top of a hash table. Where did Eclipse go? Here we go. Where's my hash code? Okay. Okay. So just like you can generate equals automatically in Eclipse, you can generate hash code. So notice that if I go to source, this is the counter class. If I go to source and I go to generate hash code in equals, notice that it doesn't let you generate just one on its own, right? It says you're going to generate both, and that's because you have to, right? If you override equals, you have to override hash code, so it gives you both of them, right? You just click what values do you want to use when you compare two objects for equality. So you'll get all of your fields here, right? For the time being, we're going to check all of the fields for equality, so we're going to use the value. Right. If you want to use instance of and equals, you just click that box there. If you want braces in your if statements, just click that box there and click generate. And what does hash code give you? Where to go? Hey, where to go? Oh, here it is. Okay. Okay, so that's the hash code that gets generated for you. That's the implementation of hash code. So there's only one field here, so this isn't that interesting, right? But it starts out picking some prime number, and it multiplies this thing called result by the prime number, and then adds your field to that value. If you have another field, it takes that result, multiplies it by a prime number, and then adds the next field to it, and then so on and so on and so on. So there's something funny about prime numbers and what happens when you multiply them together, right? So they seem to produce more or less random values, right? More or less, right? Waving my hands. So that's the version of hash code that you get. The version of equals that you get looks exactly the same as the version of equals that I've shown you. Right? So Eclipse or any other modern IDE will do all of this work for you. Okay, and so that's how you do it. There's even a slide that tells you how this works. Right? And again, this is from the same author in the same book, right? How does hash code work? Well, it uses an algorithm that yields reasonably good hash functions, right? It doesn't say it yields optimal. It turns out there is no optimal hash function, right? But it doesn't even yield quote unquote state-of-the-art hash functions, right? And notice that the last sentence here, right? Writing such hash functions is a research topic best left to mathematicians and theoretical computer scientists. Right? In other words, you probably don't want to try doing this on your own. Right? The version of hash code that gets generated for you seems to work pretty well in practice. Right? Although if you search online, you will find lots of evidence that will try to dispute that claim. Okay, so that's hash code. Right? So if you implement equals, you also have to implement hash code. Right? When you implement hash code, you have to keep something, the thing you have to keep in mind is those, right? 2 you almost never worry about, right? 2 you never worry about whether or not, well, yeah, 2 you just make sure there's no randomness in your hash code method, right? 1 is the important one, right? If 2 objects are equal, then they must produce the same hash code. Okay, compareTo. So many value type classes, like a time or a date, points, counters, they have what's called a natural ordering, right? So in other words, you can take every possible counter, right, and put it into some sort of order, right? In other words, you can sort them. Right? So in other words, for any 2 objects, x and y, x is less than y is meaningful. Right? So that's true of numbers. It's true of strings. Right? So numbers, right? Strings, you can compare those in dictionary order, but there's lots of different ways to compare strings, right? You can compare strings by their length, right? You can cook up any sort of number of ways to compare strings, right? Oh, I guess there's another thing to consider. If two strings have the same length, right, then how do you sort them? Well, then you could sort them alphabetically, right? So you can have layers of sorting as well. Right. Similarly, I guess, no, that doesn't make sense. Never mind. Okay. Dates you can compare in chronological order, right? Points, how can you compare points? Well, it turns out there's lots of ways you can compare points, right? You might want to compare them from their distance to the origin, right? You might want to sort them by their x coordinate. You might want to sort them by their y coordinate, right? You might want to sort them by any other criteria that you can think of. Right. Now, if your class does happen to have an obvious natural ordering, right, then you should consider implementing what's called the comparable interface. So this is the first time in the course that we're going to implement an interface. Right. So remember what an interface, oh wait, I probably talked about this. If you implement the comparable interface, that lets people sort lists or arrays of your type. It also lets them use tree sets and tree maps, right? Anything that needs to sort, you can now do with objects of your class. Right, so remember what an interface is? It's just a bunch of methods, right? No implementation, right? So it's just a bunch of methods and the contracts for those methods, right? So it's it just says what a class must do, right? So the comparable interface is an interface that has exactly one method, right? So we're going to create our own interfaces later in the course, right? For now, this is the declaration of the comparable interface, right? So it's public. Everybody can use the interface, right? Interfaces are always public. You can't have a non-public interface. Instead of class, you've got the word interface. You've got the name of the interface here. And then in this case, we have our generic type as well, right? So there's a generic type variable here, right? So in other words, you can compare any two objects, right? You just say what two objects you want to compare. So if I have comparable string, that's the compareTo method for the string class, right? If I had comparable point2, that's going to be the compareTo method for the point2 class. And it's got this method called compareTo that returns an int value. Right? Any class that implements an interface promises to provide an implementation of the method. So if I change our point2 class to say that it implements the comparable interface, that means I have to provide the compareTo method in the class. Right? So what does compareTo do? You just go read the documentation for it. Right? And it says it compares this object with the specified object for order. Right? In other words, compareTo is more or less less than, greater than, and equal to for objects. Right? So it returns a negative integer if this object is less than the other object. It returns 0 if this object is equal to the other object. And it returns a positive integer if this object is greater than the other object. Right? And it throws an exception if the specified object can't be compared to this object. Right? Normally, you don't worry about that. You'll get it for free. Okay, so if I want to compare points from their distance to the origin, right, how do you implement this method? So what do I need to do? Right? Well, I need to compare 2 points based on their distance to the origin. Right? So how do I compare 2 points based on the distance to the origin? Well, I compute the distances to the origin. Right? So I compute the distance from the origin for this point. I compute the distance from the origin for the other point. Right? And now I just compare them. Right? So if this point is farther from the origin, right? So if the distance for this point is bigger than the distance for the other point, I return a positive number. It doesn't say what positive number to return. It just says return a positive integer. Right? So it could be anything. It could be 1, could be 2, could be 1,000,000. Right? It's up to you. If this point is closer to the origin than the other point, you return a negative integer. Right? Again, any negative integer. Could be -1, could be -2, could be -1,000,000, could be integer min value. Right? If they have the same distance to the origin, then I have to return 0. Right? Okay. So how do you implement the point2 class so that it provides the compareTo method? Right? So number 1, go up to the class header, or I guess the class declaration. right, and change it. So I'm going to add implements comparable point2. Right? So this just says that you can compare a point2 object to another point2 object for order. That's all it's saying. Right? Now, when you say you implement comparable, you have to provide the compareTo method. So inside the class, you provide a compareTo method. Right? It has to have the exact same signature as this. Right? So it has to look exactly like that. So it's public int compareTo point2 other. Right? How do I compute the distance for a point? Right? Well, it's just x squared plus y squared, take the square root. Right? So you could write that. I'm going to use this funny method called hypot instead. Right? Hypot is just short for hypotenuse, right? Which is exactly what you want to compute. X squared plus y squared, take the square root. Right? There's already a method that does it for you. It does it better than you would probably do on your own. So I'm just going to use that. Right? Look at the documentation for hypot to see why it does it better than you probably could do on your own. Right? You're going to do the same thing for the other point. Right? I'm going to compute the distance to the, from the origin for the other point, and now I'm going to compare the distances. Right? So if this distance is greater than the other distance, return 1. Right? If this distance is less than the other distance, return -1. Otherwise, it looks like I have to return 0. Right? I have to return 0. In this particular case, this happens to be fine. Right? So this happens to be fine. But, right, there's a class called double, right, that we've already used. So you know there's double dot max value, double min value, and so on and so on and so on, double positive infinity, right? It turns out the double class also has a compareTo method, right? So we might as well just use that instead of writing all of this on our own, right? So to compare two double values, you just write that, right? So you just use double compare, right? And double compare returns an appropriate value for compareTo, right? So I can compare this distance with the other distance. Compare has the same contract as compareTo, right? It returns a negative value if this distance is less than other distance, returns a positive value if this distance is greater than other distance, and it returns 0 if they're equal, right? So we might as well just write that because it's a lot easier than writing our own if statement, right? There's also something nice about this compareTo method. Okay, now remember all that nonsense that I had to talk about when comparing two double values for equality, right? I went through probably half an hour or so of explaining why you have to use double to long bit. What the heck was it called? Double to long bits or something like that. I can't remember what the method's called exactly, right? And the reason we had to do that is because of there are special numbers defined by the floating point standard, right? There's the number called nan. And there is the fact that -0 is equal to +0 in floating point, right? When you read the compare method, though, where'd it go? Oh, it actually doesn't go through all the detail of all this. Oh, it does. Okay, so that's good. So it tells you that it uses compareTo, right? So if you go down to compareTo, which is going to be hard to find. Okay, so when you go to compareTo and you read the documentation for compareTo, you'll find that the compareTo method in the double class takes care of all the special cases for you, right? So in other words, it takes care of what happens if one of your numbers happens to be equal to not a number. And it also takes care of the special case of, 0 and -0. Right, so notice what it says. It says that 0 is considered by this method to be greater than -0. Right? So if you sort a bunch of double values in Java, right, and a bunch of them happen to be equal to 0, some of them are negative, all of the negative values get placed before the positive 0 values in Java, right, instead of them being all mixed. Right? So the way your sorting methods normally work is they're based on comparison, right? If 0 and minus 0 are equal, then they can put, then a sorting method can put them wherever they want, right, relative to one another. Java always puts them minus values first, then positive 0 values second. And so that's kind of nice, right? So you want to be consistent with the way that the Java standard library works, right? The easiest way to do that is just to use the methods that the Java standard library defines for you, right? So instead of writing that to compare the double values, right, use the double class itself to compare the double values, right? That guarantees that your compareTo method works exactly the same way as any other compareTo method in the standard library. Okay, so that's fine. Oh, yeah, I'm going to stop there. The next part gets a little bit mathematical. It's fine for you guys. For the computing scientists, it's a little harder. So for now, I'll stop there, and then I'll finish up compareTo in the next lecture. All right? Thank you, everybody.